Okay, so here is a plot of some of the sample data from the hallway and boring experiments. Now, first of all, the dashed lines that you see here, the dashed line that you see here at the bottom is what the data would look like if the subjects were just using visual angle. Now remember, in the study, let's go back here. Remember, in the study, the visual angle was identical. So in the absence of depth cues, I can't tell if this dot is here or if it's here because it's going to look identical because the visual angle is the same. And notice that's what you get here. I can't tell. It's just like it's going to be the same. I don't know where it is. I'm just using visual angle. The visual angle is the same, so whatevs, right? That's what I'm going to say. So that's a hypothetical line, right? If they were using nothing but visual angle, that's what you should get. The other hypothetical line here is the dashed line for physical size. This is the line the theoretical line that they would use if they were relying on physical size. In other words, if they had depth cues. And sure enough, when you look at the data from subject 1 and subject 2 shows that they used subject 1 and subject 2 were given depth cues, and sure enough, they were pretty good at estimating the physical size. Subjects 3 and subjects 4 were given no depth cues, so they had to rely entirely on visual angle. And notice how much closer these two lines are, the line between here and here. Notice how much closer they are to the theoretical visual angle line, which tells us that these subjects were using visual angle to try and guess how far away this was. Again, a dangerous thing to do, especially if you're a pilot flying and you have no sense of how far away things are, and you see this box on the ground and you don't know if it's a box or a building, right? One of the weird things about our universe, this is very strange. I do not understand this. This is one of those things that makes you say there must be a God, right? Because the moon and the sun have the exact same visual angle. The moon is roughly 245,000 miles away from us and 2,200 miles in radius. Whereas the sun is 93 million miles away and 865,000 miles in radius. And yet, they fit perfectly on top of each other because they have the exact same visual angle. Which again is really weird, but that's why an eclipse of the sun looks like this. Whenever the moon passes over the sun and it eclipses it, they fit perfectly on top of each other because they have the same identical visual angle. So another thing that we do in terms of our perceptual processes is we compute sizes, and we have this property of our perceptual system of size-constancy, meaning that our perception of an object size stays constant, or relatively constant anyway. So if I'm watching you walk away from me, the images of you that's being projected onto my retina is getting smaller and smaller. But you're not shrinking. You're not turning into a little tiny bug, right? I'm still perceive you as being a normal-sized human being that's simply moving further and further away from me. And we can represent this relationship in an equation. So, and this equation is S equals K times R times D. And basically what this equation is saying is the following. So S is the perceived size of something. R, and K is a constant, so it's some constant. R is the size of the retinal image, and D is the distance that you're away from me. So if you're really close to me, D is low and R is high. That makes S a certain value, right? If you're far away from me, well, D is high, the distance, because you're further, but R is low, meaning the retinal image is really small. Notice that there's an inverse relationship between R and D. The bigger D gets, the smaller R gets. The bigger R gets, the smaller D gets. And so basically they balance each other out so that we always have this perception, S, of size always being equal. So the changes in the distance and the size of the image on the retina balance each other out. And this tells us why this little equation gives us a good picture, I think, as to why we need distance cues in order to judge relative size, or why a pilot would need distance cues to judge, whether that box on the ground is a box or a building. So here's an interesting thing known as Emmert's law, and it's kind of neat. So if you've ever been had a bright like a flash go off in your eye, or a bright light briefly shined, one of the things that you notice is you see an after image, right? So you look away, so you get so a flash goes off, and then you blink, and if you look away, you can still see that flash for a few seconds afterwards. If I have somebody right in front of me take a picture with a flash, right? So boom, the flash goes off, and I have these little dots. If I look away, that dot, that spot that was originally right in front of me, does not change size. It gets projected. So if I look away, if I look away from where the flash was, and I look at a wall that's a distance from me, that dot stays the exact same size on my retina. So what does that mean? Well, when the flash was right in front of me, I had good depth cues, right? Because I could see the person in front of me. Then they flashed me, right? Then I look off at a wall in the distance, and I see that same size dot on that wall over there. Am I going to perceive that dot as the same size, or bigger, or smaller? I want to perceive that dot as bigger, because it's the same size on my retina, but I'm looking further away. And for those couple of seconds that it's on my retina, I'm looking further away. I'm going to perceive it as being larger simply because I'm projecting it onto a further thing, and it follows the rules that we saw in this equation before, meaning that the distance increased, but the retinal image stayed the same. So if the distance increased, that means the perceived size S also increased. And for that few seconds, when you look from where the close camera was and then where that dot is now sort of like floating on the wall at a distance, it's going to look like that dot's a lot bigger, simply because you're projecting it onto a further thing that's further away. In this picture here, the retinal image that is projected from this tree is bigger than the retinal image that is projected from this tree. So on my retina, this tree is bigger than this tree. However, we perceive that these trees are all the same size. And the reason we perceive that is because we have lots and lots of depth cues here. We have this street running by. We have the buildings that are decreasing in size. These benches here and the bikes over here that look fuzzy. We have a lot of depth cues here that tell us that this guy and this guy are probably about the same size. Now, if you were to just completely remove all of those depth cues and just have those trees on a white background, we wouldn't know that this might be a bigger tree and this might be a little bitty tree. We don't know. And here's a picture of the Emmert's law. So let's say I somehow stare at a dot for a really long time and then burn it into my eye. and then look away real quick. If I look away at a wall, say for example, well, that dot is going to have the same visual angle as the dot that was on the book. But since I know that the wall is further, since I know that the wall is further away from me, I'm going to perceive that dot as being much larger than it was originally in the book where I burned it into my eye. Here's a good, you've seen these things before, right? This I guess is a gigantic, I don't know what that is, but anyway, how do we know, how do I know that this is a gigantic whatever? Well, the way I know it's a gigantic whatever is because there's a person standing next to it. And that person is giving me the cues that I need to be able to tell me how big that object is. So here's another example of some cues that we use in size constancy. These two cylinders look the same, and the way we know that they are in fact probably the same size is the fact that they both cover the same amount of space of a brick here. So this is about as wide as this brick, and this is about as wide as this brick. And we know that the bricks are arranged in different distances from us because of the fact that the grouping of these bricks has bigger spaces than the grouping of these bricks, which has smaller spaces, and these bricks are much more clearer than these bricks, which are kind of fuzzy. So we know that these bricks are closer to us than these bricks, so we have that distance cue. And we know that this can is about as wide as this brick, and this can is about as wide as this brick. Therefore, we assume that the cans are of equal size. There are a lot of different visual illusions that you can use to trick your visual system into seeing depth and seeing things that aren't really there. Because our brains have these mechanisms for computing depth, and you can take advantage of those in visual illusions. One of the more famous ones is the Mueller-Lyer illusion. Which is this one here. So basically, the illusion is that the line that is on this line here, that is on your right, is actually longer than this line here, when in fact they're not. Actually, they're the same size. Now, the reason this line looks longer is because we are perceiving this line as an edge, an inside edge. So we're standing inside of some room or whatever, and we're looking at the walls converging like this. So it looks like the line is further away. But in this image here on the left, it looks like we're looking at a corner. So we're standing outside, looking at this corner that is kind of coming at us and closing up like that. So we're perceiving it as being closer to us, right? So since it's closer to us, and this is further away from us, we are perceiving this one as being much, much bigger, or bigger anyway, because it's further away, but yet it looks like it's about the same size. So the visual angle is the same. So since it looks further away, this one is probably, oh darn it, sorry, this one's probably bigger than this one is, when in fact they're the exact same size. So here's another, and this is the perceptual apparatus that we're using in the Mueller-Lyer illusion. We're using this detection of outside corners and inside corners. So this would be your outside corner, and this would be your inside corner. And we typically perceive outside corners as being closer to us than inside corners are. And since inside corners are further away, but it's painting the same length as this one, we assume that this line is longer than this line.